Hello, this is 4.3, Determining Statistical Significance. We will start this section with an example from 4.2. So in testing, we have the null hypothesis p equals 0.5 versus the alternative hypothesis p is less than 0.5. The observed sample proportion p hat is 0.35. Based on the randomization distribution above, the p-value is, and we need to make a choice. Obviously, we will ignore for a second that we can see the answer, and let's try to do it ourselves. So if you look at the alternative hypothesis, you notice that this is p less than 0.5, so you know this is a left tail test, so you're looking to the left side, and what you do is you're gonna take the sample statistic 0.35 and look how extreme is this sample statistic. So if I look at 0.35, I see only one dot to the left of it, and that's one dot out of 1000. So the p-value will be 1 out of 1000, which is 0.001. Another example we did also in 4.2 was this example, and the whole idea behind this example was to show that the further we are on the tail, the smaller the p-value will be. So in our case, we had 0.5. This was the furthest of them all, and it was matched with the smallest p-value. Then the new idea that we want to emphasize in 4.3 is that not only the further it will have a smaller p-value, but the smaller p-value will actually provide a very strong evidence against the null. So if the p-value is small, then statistic as extreme as the observed would be unlikely if the null hypothesis were true. So basically, if you have a smaller p-value, then you have a very strong evidence against the null hypothesis and in favor of the alternative. Basically, you're saying that in a null situation, this can rarely happen. So the null situation is wrong, and there must be something else alternating with my result. And that's why basically we always hoping to have a small p-value. So let's see some examples. Which of the following p-value gives the strongest evidence against H0 or the null hypothesis? So we just said that the smallest p-value will give me the strongest evidence against the null hypothesis. So from those options, I have 0.005 is the smallest p-value. Now the same question can be asked differently. They can ask you which of the following p-value give the strongest evidence for the alternative. So it's either for the alternative or against the null. And again, in both cases, you're looking for the smallest p-value. In this case, it's 0.03. So when we do hypothesis testing, we need to make a formal decision, and we always have two possibilities. Either the p-value is very small and we reject the null in favor of the alternative, or the p-value is not small and we don't reject the null and we say the results are inconclusive. Notice how when we didn't reject the null, we did not accept it either. So you either reject the null and you accept the alternative, or you don't reject the null and you just say that results are inconclusive. So let's look at different situations. Let's look at this one here. You have the randomization distribution. The sample statistic is 0.6 and the p-value was 0.001. Based on this randomization, do you think we should reject the null? We look at this p-value is very small, so we're going to say yes. Here's another situation. This is the sample statistic, and this is the p-value, and look how much it's covering from the randomization distribution. So based on the randomization distribution, do you think you should reject the null? Basically, is the p-value small? And in this case, it's obviously it's not, so we're not gonna reject the null. How about this case? This is not as small as 0.001 and it's not as big as the previous one. It's in between. So should we reject the null or not? How small p-value needs to be? So we need to determine basically the cutoff. And that cutoff, we will call it, this is the new term, we call it the significance level. Significance level denoted by alpha is basically what tells me how small the p-value is. So either p-value is less than alpha or larger or equal to alpha. If p-value is less than alpha, then we reject the null. And if p-value is larger or equal to alpha, we don't reject the null. Now alpha should be stated or given to you whenever you are given a problem. If it's not given to you, the number that we usually use is 0.05. So it is always 0.05 unless otherwise stated differently. And there is a reason why this is the normal number for us. You can watch this at your time. And it is provided to you in the PowerPoint. So when p-value is less than alpha, we call our results statistically significant. So whenever you have statistically significant result, you can actually say that you have a strong evidence in favor of the alternative and against the null. So here are the two situations. Either the p-value is less than alpha, and this means results would be rare if null were true, and that will lead to rejecting the null. And we can say that we have evidence that the alternative is true. These results will be statistically significant. Or p-value is larger or equal to alpha, and in this case we will say that results wouldn't be rare if the null were true. We don't reject the null, we don't accept it either, and we say our test is inconclusive. And in this case, our results will not be statistically significant. In this case study, we're looking at the resveratrol, which is an ingredient in grapes that has been shown to promote weight loss in rodents. Specifically, we're looking at lemurs. So you have a sample of lemurs, and they were measured first, then randomly assigned resveratrol supplementation for 4 weeks to see if there was any difference in their body mass. So let B be before resveratrol supplementation and A after resveratrol supplementation. For the test involving body mass and food intake, what are the relevant hypotheses? So first we need to think what variables do we have to build these hypotheses. The first variable you have is their body mass before and after, and that's a quantitative variable. The second variable you have is the resveratrol supplementation before and after, and this one is a categorical. Whenever you have a categorical and quantitative variable, you will use the difference in means. So to write the hypothesis, you have the null, the mu b, which is the body mass mean before resveratrol supplementation, is equal to the mean after. And this is as usual in the null, we use the equal sign. The alternative, we're trying to prove that they actually lost weight, so their mass before is larger than their mass after. So in the test, to see if the mean body mass is lower after treatment, the p-value is 0.007. Using alpha 0.05, we should. So again, if p is less than alpha, we reject the null. If p is equal or larger than alpha, we don't reject. In this case, p-value is less than alpha, so we reject the null. Now, what can we conclude? What does that mean? It simply means that the body mass is lower after the resveratrol supplementation. We rejected the null. The null was saying that their body mass did not change. So we rejected that in favor of the alternative, and the alternative that we said that it's going to be lower after the supplementation, or we can say it was larger before the supplementation. Here's another case. Let's say we had a p-value equals 0.007 and alpha was 0.01. In this case, would you say this is statistical significant? So again, statistical significant means the p-value is less than alpha, and in this case, p-value is larger than alpha. So these results are not statistically significant. So Just a reminder, we never accept the null. We never. When we don't reject the null, we simply say that our results are inconclusive. So when you write conclusions, you need to make sure that you're writing it correctly. So if p-value is less than alpha, then we reject the null. If p-value is larger than alpha, then we don't reject the null. So the first step is whether we reject the null or not. When we write the conclusion, however, we are thinking of the alternative. So we're either saying we have strong or not strong evidence in favor of the alternative, or we just say we don't have enough evidence to conclude the alternative is true. Basically, we're saying our test is inconclusive. So first step is rejecting or not rejecting the null. The second step is either concluding that the alternative hypothesis is true, or we have evidence to prove that it is true, or we don't have enough evidence, so our test results are inconclusive. So here So this is the most important slide because it sums up everything that we've covered in 4.1, 4.2, and 4.3. Every time they ask you to provide evidence or to prove something, you need to do these 5 steps. First, you need to state the hypothesis, and in here you will state the null, the alternative using the population parameter. Second, you need to find the observed sample statistic calculated. Third, you need to find the p-value, and we will be using StatKey to find the p-value. You need to figure out, is this a right tail, left tail, or two-tail test, and using the StatKey, and then find the p-value. 4, you need to make a generic decision. Do we reject the null or we don't reject the null? Either one. 5 is you need to write the conclusion, and when you are writing the conclusion, you are writing it in terms of the alternative. So you're basically saying we have enough evidence to prove the alternative, or we don't have enough evidence to do that. So let's see an example. So until 2002, hormone replacement therapy, HRT, was commonly prescribed to postmenopausal women. This changed in 2002 when the results of a large clinical trial were published. So in this study, 8,506 women were randomized to take the HRT, and 8,102 were randomized to take placebo. 166 using the hormone replacement therapy, and 124 taking the placebo women developed invasive breast cancer. So since the numbers using the hormone therapy were higher, they had this question: does the HRT increase risk of breast cancer? Now again, remember, whenever we want to prove something or provide evidence, we need to go and do those 5 steps. So the first step is constructing the null and the alternative hypothesis. And for us to do that, we need to know what kind of variables do we have. So the first variable is that which kind of treatment they did take. So either a hormone treatment or the placebo one. And this is a categorical variable. The second variable is if they developed invasive breast cancer or not. This is also a categorical variable. So you have 2 categorical variables. It means we will use difference in proportions. So when we write the null and the alternative hypothesis, first we want to make sure that we are explaining our notation. So P1 is the proportion of women taking the HRT who got invasive breast cancer, and P2 is the proportion of women who are not taking HRT and got the invasive breast cancer. So the null will say that there are no effect to what kind of treatment they got. The proportions should be the same. The alternative will follow the question, and here you have the question, does the HRT increase the risk? So when you write the alternative, you will put the larger sign. You're saying I need to prove if P1 will actually be always larger than P2. Step 2 is calculating sample statistic, and for us we had a difference in proportions, right? So our sample, here you have P1 representing women who took the HRT out of all the women who got the breast cancer, out of all the women who took the treatment. And here you have the number or the of women who got the breast cancer out of all the women who did not take the HRT. So the difference in proportion in our sample statistic is 0.0042. Now step 3 is finding the p-value, and as I said, to find the p-value you need to go to Statistical. So you'll go into the randomization hypothesis testing, right, and you will pick the one that goes with what are you looking for. So this is difference in proportion, so I need to edit my data. So for my data, group 1 was the number of women who got cancer after taking the hormone therapies, and those were 166 out of 8,506. And group 2 were the women who got the breast cancer after taking the placebo. So there was no hormone given to them, and those were out of 8,102. And once you enter this information, you'll see it in this box here. You see group 1, group 2, and the difference in proportion is given to you in your sample statistic. So it is exactly like what we got. Now, after that, you start generating samples, and then you need to make the decision, is this a right tail, left tail, or two tail? This is obviously a right tail because the alternative P1 is larger than P2. And then you will make sure that you have a sample statistic over here. Now, notice once I'm going to enter this, the p-value could be different a little bit between you and me. So this might a little bit change, but it should be almost the same. So I'm going to enter the correct sample statistic that I'm looking at, which is 0.0042. And when I did that, I got 0.022. Now you might get something slightly different, that's totally fine. When I created the PowerPoint, I had a slightly different number, but this is basically the p-value. So previously, when I did that, I got a p-value that is close to the one I just got. So if I round this up, this will be 0.02, which is also similar to the one that I just got. But in any case, your p-value is always using Statistical, using the same method. You'll go, you make the decision which direction your test is, and you plug in the sample statistic, and that will be your p-value. Now, step 4, you need to make the generic conclusion. Basically, should we reject the null or not? So alpha, as we said, if it's not given to you, alpha will be 0.05, and obviously in this case my p-value is less than alpha, so you reject the null. Step 5 is making the conclusion. So when you write the conclusion, you're keeping the alternative in mind. So in this case, we will say that we have convincing evidence, since we rejected the null, we have convincing evidence that taking hormone replacement therapy does increase risk of breast cancer. So as I said, this was a true experiment, and after that experiment, they actually stopped using that treatment. It's no longer recommended in the US. Okay, your turn. Let's try, I need you to try this example before you see the solution. But in this case, here are the numbers. So you have 8,506 women were randomly given the hormone therapy. 8,102 were not, were given placebo therapy. And 502 out of the women who were taking the hormone therapy developed breast cancer. and 458 out of the placebo group developed breast cancer. And the question was, the question is, does hormone replacement therapy cause increased risk of cancer in general? So try this by yourself before you see the solution. So here is the solution. So first step is stating the hypothesis. The null will have the equal sign. The alternative will follow the question. So you'll have P1 larger than P2. Step 2, find the sample statistic. And this is difference in proportion. So you found this. You find this by yourself. And then step 3 is finding the p-value. And for that one, you need the stat key. And once you go to stat key, you click right tail test, and the p-value, as I said, might be a little bit different, but it should be very similar. And then you need in step 4 to make a generic decision, basically by comparing the p-value to the alpha, and in this case, the p-value is larger than alpha, so we don't reject the null. And step 5, the last one, you need to write a conclusion in terms of the alternative. So in this case, we will say we don't have convincing evidence that the hormone therapy increases the risk of cancer in general, because we did not reject the null. So in summary, the summary for 4.3, so the new thing that we introduce is the alpha. Alpha is what we call the significance level, and this is basically what determines if my result is statistically significant or not. And the way we do that is by comparing it to the p-value. And once we compare it to the p-value, we make formal decision. We either reject the null or we don't reject the null. Keep in mind, when we don't reject the null, we don't accept it as well. And finally, whenever we write the conclusion, we always want to make it about the alternative. So either we have enough evidence or we don't have enough evidence. And this concludes 4.3.